Okay, so we're going to do a review today, and then I'll explain the homework. So first, review of basic matrix methods and LU and QR decompositions. Okay, so vector norms, this is the general definition of a vector norm. P can be anything from 1 through infinite. And this in particular is the Euclidean or the L2 norm. This is the triangle inequality. The norm of x plus y is less than equal to norm of x plus norm of y. And then this is the Cauchy-Schwarz inequality. The norm of x transpose y is less than equal to norm of x times norm of y. Notice the similarity between the two. This is inner product. It's a kind of multiplication, right? So this is with the plus, and this is with the multiplication, addition and multiplication. They're analogous. And these are matrix norms. Matrix norms are induced norms. So what we do is we try to maximize the norm of AX when X is a unit vector. And this is Holder inequality. L2 norm is less than equal to square root of L1 norm and L infinity norm. You know the L1 norm and L infinity norms. One is the row column, row maximum, one is the column maximum. Okay, this is the one norm, and this is the infinite norm, which I just said. This is the Frobenius norm, which is also equal to the trace of A conjugate transpose. The L2 norm is equal to sigma 1, singular value. And the Frobenius norm is square root of, take the summation of all the singular values, add them up. And then take the square root of that. That's the Frobenius norm. Unitary matrix, we know that the columns of a unitary matrix are mutually orthogonal, and they're all unit vectors, which is why Q transpose is the same as Q inverse. All the eigenvalues, they can be complex eigenvalues because it's not necessarily symmetric. In fact, most of the time you'll see that the unitary matrix is not symmetric. The only unitary matrix that's symmetric is the identity matrix, by the way. So they would have complex eigenvalues, but the absolute values are all unity. In other words, they lie on a unit circle. And that's why the norm of Qx equals norm of x, where Q is a unitary matrix. So Q does not affect the vector norm. And likewise, Q does not affect the matrix norm either. Determinants and condition numbers. So determinant of AB is the product of the determinants of A and B. Determinant of A inverse is 1 over determinant of A. Determinant of a lower triangular matrix is the product of the diagonal elements. Determinant of an upper triangular matrix is again the product of the diagonal elements. And determinant is also the product of the eigenvalues, which is also equal to the product of the singular values. Of course, A has to be a square matrix. Determinant of Q is +1 or -1, where Q is a unitary matrix. Condition number of a square matrix A is norm of A inverse times the norm of A, which is also sigma 1 and sigma n are the singular values, so sigma 1 divided by sigma n. Quadratic form, if this is f of x, a function of x, then its gradient, the first derivative, is equal to this. And Q need not be symmetric, but x transpose qx and x transpose q transpose x would give you the same values. So this is a scalar quantity, and it doesn't matter if q is replaced with q transpose. And so this is the gradient. What you're doing is you're taking the, making the matrix symmetric here. So this is the gradient, and this is the Hessian, the second derivative. And for a symmetric Q, this is the derivative Qx plus P, and second derivative is simply Q. Now we actually go to LU, PLU, and LL transpose decomposition. So LU decomposition is what we do is each time we do a row operation, it's like pre-multiplying with a lower triangular matrix. So we do n-1 row operations, and so that's equivalent to multiplying by m1, then m2 until n-1. And the product of all these lower triangular matrices is also lower triangular, and let's call this product of all these mn-1 through m1 equal m. So ma equals u, and m is also lower triangular. And I've already told you that inverting a lower triangular matrix is much simpler, easier, computationally speaking, than any other matrix. Therefore, L equals M inverse is not hard to compute, and so MA equals U implies A equals LU. This is what LU decomposition looks like. PLU decomposition. PLU decomposition is sometimes you rearrange the rows of A, and we assume that it's done a priori, not within the algorithm, in which case P is a permutation, P transpose is a permutation matrix that does the rearrangement of the rows of A, and then we take P transpose A and perform LU decomposition on that, whence we get A equals PLU, because P transpose is the inverse of P. Cholesky decomposition can be applied only when A is positive definite, in which case this is the decomposition. A equals LL transpose or A equals U transpose U. L is a lower triangular matrix and U is an upper triangular matrix, like this and this. QR decomposition. So this is full QR decomposition. This is a matrix. I'm assuming it's a tall matrix, I mean a long matrix. So this is the full QR decomposition. Q is a unitary matrix, and R is upper triangular and with a bottom section, all zeros. And since Q is unitary, we have Q transpose equals the identity matrix. Q transpose Q is also the identity matrix. Reduced QR decomposition is we take off the rightmost columns of Q, and this is a reduced Q, it's not even a square matrix now, and we take off all these zeros at the bottom, so R is strictly a upper triangular matrix, and so now Q is, since I've taken off columns, it has less columns than rows, correct? So Q transpose cannot be equal to the identity matrix because the inner dimensions of this product are less than the outer dimensions. But Q transpose Q, because the column vectors are orthogonal, is equal to the identity matrix. This is the lower dimensional identity matrix. Over determined systems. So the least square or min norm solution is like this. We have AX approximately equal to B. A is a tall matrix, so we have more equations to satisfy than variables X. And so we take the remaining, the residual or the error, R equals B minus AX, and we try to minimize phi of X, which is R transpose R. So this is phi of X when you replace R with B minus AX. This is what you get. And differentiating, we get this. The first derivative must be equal to 0, and the second derivative must be positive definite. And you can see that the second derivative is positive definite here. And so we get the solution is, when we try to minimize this, we get the solution is A pseudo inverse B, where A pseudo inverse is equal to this. And I did not include here for underdetermined systems, but for the underdetermined system, again, there we are trying to match AX to B, but there are multiple solutions when A is a wide matrix. In that case, the min-norm solution would min-norm of X. We're trying to minimize min-norm of X subject to AX is exactly equal to B, if you remember the derivation, in which case A pseudo inverse will be A transpose times AA transpose inverse. So A transpose first and then AA transpose inverse. Okay, so now using QR decomposition, what we do is we take A, and this, what I'm showing here, is the full QR decomposition of A. That's why I have the 0 at the bottom. So this is what I'm trying to solve. Implies, since the inverse of Q is Q transpose, so this is equal to R0x is approximately equal to Q transpose B, which is C1 and C2. Okay, and then what I do is I simply ignore the, if I read the bottom portion of this expression, 0x is equal to C2, or 0 equals C2. I cannot satisfy that because I have no variables. So ignore the second part, the bottom part, and just look at the first part. Rx equals C1 when x equals R inverse C1. So the QR decomposition actually is the same as the least square solution. This is the argument, the function that I was trying to minimize, and this function, we have shown that this is equal to this function. It can be expressed in this manner. And C2, obviously we have to ignore. All we can strive to do is satisfy this part, make C1 equal Rx so that this becomes 0. Now, if you were to use reduced QR decomposition, then you would straight away get QR equals B, or R equals Q transpose B. Sorry, I mean Rx equals Q transpose B, which is equal to simply C1. You wouldn't get C2 if you do reduced QR decomposition. The 0 won't be there. So instead of full QR decomposition, you can use reduced QR decomposition and you'll get the same expression. C1 is Q transpose B from the reduced QR decomposition. Gram-Schmidt orthogonalization. So at the kth iteration, everything here is known. We have a matrix A, and we are trying to do reduced QR decomposition on A. So this matrix A is known, actually. These are the ones that I've used, and this AK is the one that I'm going to use. The kth column on this side, the kth column on this side, and the kth column here. Okay, so I'm concentrating on the kth columns. So this is the Gram-Schmidt algorithm. So I first determine these non-diagonal elements. These are in red, they are unknowns. Everything that's in red is unknown in the kth iteration, which we're trying to find. So I get Rik equals, for each of these, Rik equals Qi transpose. Qi is one of these, which is known, so Qi transpose, and Ak is obviously known. So all the A's are known, so Rik I get. And then I forgot to write here, Yk I initialize to 0, a 0 vector. And then, what was Yk equals, Ak. I initialize Yk to Ak here. And then, right here, I should have another statement here, Yk equals Ak. And then I keep subtracting from yk in each iteration one of these rik qi's. So what happens is at the end, the remainder, which is the component of ak along qk, will be yk. So since yk is any vector along the direction of qk, unknown qk, but once I've determined y, the norm of y, the length of y is rkk, and a unit vector along the direction of yk is the qk. Any questions? Which one? Slide number 10. This one.
You said about using QR reduced and QR full.
Okay, this is the derivation that we did, which is full QR decomposition.
Is there any advantage of using full and then reduced?
No. No.
Again, even if we are using full, we are ignoring C2. So,
yeah, it's equivalent to just using reduced. Why not use reduced?
Yeah,
that's all. Understood?
Yeah, both are same.
Yeah, both will give you exactly the same answer, which is the same answer you would get from the pseudo-inverse method.
So preferably we can use the reduced one.
Yes, computationally, it will be wasteful to use the full QR. But when you're doing some derivations, it's always handy to have Q be a unitary matrix. Okay. So, so now we'll do spectral and single value decompositions. Matrix spectrum, by definition, V is an eigenvector and lambda is the eigenvalue if they satisfy AV equals lambda V. And the way V, all the eigenvectors are normalized so that they're unit vectors. And the indexing is such that lambda 1 has the highest numerical value, then lambda 2, until then lambda 3 until lambda n, or whatever, some might be repetitive, some eigenvalues. So these are the eigenpairs. And like I said, eigenvalues could be repetitive. So this is the characteristic polynomial. And how we get the eigenvalue is by equating the characteristic polynomial to 0. The roots of the characteristic polynomial are the eigenvalues. And the characteristic polynomial might have multiple roots, lambda I. Mu I could be 1, 2, 3. So mu I, lambda minus lambda I to the mu I is one of the factors of the characteristic polynomial. And mu I here as mu of lambda I is the algebraic multiplicity of the eigenvalue. The number of times lambda I repeats. But the eigenvectors, even if you have multiple lambdas, same value, the eigenvectors would be different in general. Okay, so in which case, if all the eigenvectors are different, even if lambda I is repeating, then the geometric multiplicity will be equal to the algebraic multiplicity. Otherwise, the geometric multiplicity, so here is the geometric multiplicity, is the number of linearly independent eigenvectors Vi of lambda I. So if for every eigenvalue, if the algebraic and geometric multiplicities are the same, then it's a non-defective matrix. In general, algebraic multiplicity will always be greater than or equal to the geometric multiplicity. And otherwise, if this is a strictly greater than for any eigenvalue, then the matrix is a defective matrix. You might have heard of Jordan matrices. That's how to deal with this situation. Defective matrices. Anyway, matrix spectrum properties for a Hermitian matrix. Its conjugate transpose is equal to itself. That's a Hermitian matrix. It has real eigenvalues. And a real symmetric and non-defective matrix is this. The eigenvectors will be real and orthogonal. Similarity transformation, A and B are two similar matrices under this T. So eigenpair of A, let's say, is lambda V, then the corresponding eigenpair of V is, so the eigenvalue does not change, the eigenvector, you have to pre-multiply the eigenvector with T inverse. Shifts, what does shifting do? Shifting is like subtracting this sigma from only the diagonal elements. So what it does is it shifts the eigenvalues. So if A is eigenvalue is lambda, it's the eigenvalue of B would be lambda minus sigma. The eigenvalues would be shifted, but the eigenvectors remain the same. Inverse. For an eigenpair lambda B, what will happen? A inverse 1 over lambda will be the corresponding eigenvalue. Eigenvector does not change. So this is spectral decomposition. V is the matrix, a square matrix of all eigenvectors. Its columns are the eigenvectors, and lambda is a diagonal matrix of all eigenvalues. So what the spectral decomposition theorem says that lambda is equal to V inverse AV, or A equals VA. Sorry, this is lambda. This is this lambda here. It's a typo, V inverse. And for a symmetric matrix, V inverse is the same as V transpose. In other words, V is a unitary matrix. So this is how we can decompose a symmetric matrix in terms of n rank 1 matrices, lambda I, Vi transpose Vi. And so this is what happens. All I've done is V inverse is now replaced with V transpose. In both these cases, I just copy pasted. So this A got copy pasted here. This is actually lambda, this matrix. Okay, and we've seen that A to the K is V, lambda to the K V transpose. E to the A is V, E to the lambda times V transpose. Here you can do the exponentiation element wise. This E to the A, you're not exponentiating each element. This is based on the Taylor series expansion. I plus A square over 2 plus A cube over 3 factorial and so on. Likewise, here we are not doing element-wise raising it to the power of K. This is for the whole matrix. A square is not equal, U is A times A, it's not equal to each element of A would be separately squared. You understand the difference. Anyway, so any questions so far? So a positive definite matrix, Q is positive definite, positive semi-definite if lambda is greater than or equal to 0, and you know that equivalent definitions of negative semi-definite and negative definite, positive definite matrices. Rayleigh quotient, something that we did in an example. Okay, next we go on to singular value decomposition. So this is a full SVD, and this is for a tall matrix, a long matrix, tall matrix. What do I use? Tall matrix, right? Or what do you call it? tall matrix. A tall matrix, and this is the SVD, and U and V are unitary matrices, and this sigma is diagonal matrix of all the single values, and then you have a bunch of zeros at the bottom. And this is what we do is we take off some of the rightmost columns of this U. So this is U1 through UN. M is more than N. This is an M by N matrix. M as in Maryland, N as in New York. So this becomes also a tall matrix of the same shape as A, and then we don't have to use this bottom all zeros. So this is strictly a diagonal matrix, and B remains the same. This is reduced SVD. And just like in spectral decomposition, in exactly the same way, singular value decomposition can be used to express any matrix now. It can be a tall matrix or a wide matrix in this format. Summation I, sigma I, ui, vi transpose. By the way, all the sigmas are strictly greater than 0, and sigma 1 is the the largest one, then sigma 2, then sigma 3, and so on. So SVD properties, A inverse is V diag of 1 over sigma. So it's the diagonal matrix of 1 over sigmas and U transpose. Singular values of sigma I are the roots of the eigenvalues lambda I of A transpose A or A transpose. For a tall matrix, A transpose A would give you the non-zero eigenvalues. But A transpose for a tall matrix would have a low rank. It won't be full rank matrix. So it will only have N as in New York non-zero eigenvalues. The other eigenvalues would be all zeros. Okay? So you can take the non-zero eigenvalues, that would give you all the sigmas. Low rank approximation. This is, I should have made it uppercase N. So this is A equals to this. What I do is I only take the first R terms, and then I get the reduced rank or low rank approximation of A. That's A tilde. And we have a theorem. It's a theorem, but I've explained it well in a YouTube video. So just look at that theorem. For the name, look at Young is the middle one. Eckert, Young. Mirsky. Right?
I don't know. Some young, I don't know.
Yeah. Anyway, so that theorem, I explained it quite well with some nuances of the proof. So take a look at that. So I had explained it in A7, lecture number A7, but I did that again for your benefit because you might not have gotten everything. So I went back and did it. Anyway, so this is geometric interpretation of the eigenvalues and eigenvectors. So let's say this is X. It can be expressed in terms of the VIs, the eigenvectors, which are orthogonal. I'm assuming that Y is a square symmetric matrix. X can be expressed as a linear combination of the eigenvectors of the matrix A, and let's say Y equals AX. So Y is another vector. then so alpha i's are the coefficients of vi's. So when we do this multiplication, so the coefficients of y would be lambda I sigma I. And the norm squared of y would be summation lambda I squared alpha I squared. The norm of x would be summation alpha I squared only. So this is what happens. The highest amount of stretching from this expression, to get the highest amount of stretching, you would need to, let's say we are confined to a unit vector. X is a unit vector, in which case we make alpha 1 equals 1 and all the subsequent alphas equal to 0. That would make x equals v1 and y equals alpha 1 v1. That gives you, lambda 1 v1. And since lambda 1 is the largest eigenvalue, so we get the maximum stretching. This is v1, x equals v1, then y equals lambda 1 v1. It's stretched by this amount, lambda 1. Next, we want to look for another direction which maximizes the stretching, but it must be orthogonal to v1. So the answer is make alpha 2 equals 1 and the other alphas equal 0, and hence you get x equals v2, alpha 2 equals 1. So we get v2 and y equals lambda 2 v2. So this is x is v2, y is lambda 2 v2. And likewise, we want something that's orthogonal to both v1 and v2. The answer is the third eigenvector v3. When x equals v3, y equals lambda 3 v3, and so on. The directions won't change when these are the eigenvectors. Otherwise, there will be some change, rotation, or something. Okay, now geometric interpretation of SVD. We take any arbitrary matrix. So this is y now, and this is the norm of y. Now instead of lambda i's, I have all the sigma i's. That's the only difference. And so the directions of the direction of maximum stretching is v1, but that would be x. Y would be sigma 1 u1. Then if we want another direction that's orthogonal to v1, the answer is v2, x equals v2, and y equals sigma 2 v2, blue and blue. See, the directions are changing because this is a v and this is a u. Here's an example of singular value decomposition. This is x, and I have to choose alpha 2 and alpha 3 such that x remains a unit vector. Alpha 1 is given to me. So I want to minimize ax subject to x being a unit vector, and alpha 1 is already known. So we have to find alpha 2 and alpha 3. So the minimum stretching occurs along v3. So we have to set alpha 3 equals 1. Alpha 2 equals 0, and what we get is root 2 over root 3. Not 1 over root 2, root 2 over root 3. Sorry, I've written it here. This is a typo, root 2 over root 3. By the way, for a square matrix, is the eigen decomposition equal to the singular value decomposition if it's a square matrix? No, because for any square matrix, lambdas can be negative or complex, right? So the answer is no. If the matrix A is a symmetric matrix, then would you say that the spectral decomposition and the singular value decompositions are the same? No, again no, because if it's a symmetric matrix, we know it has real eigenvalues, but nonetheless, the eigenvalues could be negative. Correct? But singular values are always positive. So, again, no. For a positive definite matrix or a positive semi-definite matrix, what can you say? In that case, yes. And that's from the uniqueness property of singular value decomposition. Because the spectral decomposition, let's take a positive definite matrix, A, or positive semi-definite symmetric matrix A. We do the eigen decomposition. It has the same format as the SVD, correct? But the spectral decomposition, the singular value decomposition must be unique, which means that the two are equal. Did you understand that part? Okay, so we went through this, and so there was a typo here. Now we'll do PCA. I have the videos of lecture A8 and A9. I hope you have already seen it. The derivations are there. Fisher's linear discriminant analysis is a little complicated, so do pay attention to that. So, but I'll do PCA only here in this review. I won't focus on LDA because we would run out of time. So what is dimension reduction? So I'm choosing a direction which gives us the maximum variance. I'll explain. So these are n-dimensional points. Here it's in 2 dimensions. There's a scatter plot. And I want to convert 2 dimensions to 1 dimension. Okay, and let's say I have to choose a unit vector, and I have to choose a direction, more in general terms. I have to choose a direction. This red dotted line is a direction. So V is a unit vector along that direction. So how do I do my dimension reduction? So each point x, which is like a vector from the origin to this point. Okay, so x is a vector. V transpose x is the length of this. Okay, that's the projection of x along V. This is the projection of another point along V. And this is the projection of yet another point along V. And so what I do is, so I project all the points along V. I get, this is my one direction. From 2 dimensions, I reduced the data to 1 dimensions. Reduced dimension is so 1 dimension. And I can take this as my coordinate now. And so this is what the points look like in 1 dimension. Now, if I had taken some other direction, like this or whatever, then I would have gotten some other like 1-dimensional scatter plot here. But what did I do here? I chose this direction and hence this vector V, so that the variance of the projected points would be maximized. Okay. So you see, they are quite spread out, all the red dots. For some other direction, it won't be that spread out. So the variance would have been less. So my goal is to do dimension reduction that would maximize the variance. Okay. So now, here's what we do. First, what we do is, data pre-processing. It's usually better from a data science perspective if the points are centered so that their mean coincides with the origin. So how do we center the data? These are the points. Each sample is d by 1 vector, and I have n samples, n being much higher than d. So I take all the points, they are transposes, and this is the data matrix. It's an n by d matrix. I have to do this transpose operation, okay, the way I've formulated the homework. And the mean is x hat. This is the sample mean, is 1 over n times summation xn. Now, how do we do centering? Each point, we have to subtract the mean from it. That will move the point, okay, by this amount, x hat. And in terms of the matrix X, this is what I'm doing. And this tells you why it happens. So this is what you can do to center the data. So before centering, this is what the data looked like, and it follows some high-dimensional Gaussian distribution, let's say. So after centering, this is what happens. It moves all the points so that the sample mean, or the sample average, coincides with the origin. If the data is sparse, like if you have let's say you have quite a few dimensions, but relatively low number of sample points, then the actual mean of the Gaussian distribution would not be same as x hat. So you have to do this translation of all these sample points using x hat, the sample average, the sample mean, instead of mean, even if you know the Gaussian mean or some other distribution mean. Okay, then we'll do principal components, apply principal components. We obtain the covariance matrix of all our sample points. Again, this is the sample covariance matrix, not the covariance matrix of the Gaussian distribution. Okay, so this is the sample covariance, and MATLAB has commands COV does covariance, but you can also use my expression. First of all, the covariance matrix is positive semi-definite or positive definite, unless along one dimension everything is constant, 1, 1, 1, 1, 1, 1, 1, 1 along one axis, or 2, 2, 2, 2, 2, 2, 2, 2, 2, or 3.5, and so on. So if one of the dimensions is constant, it has no variations. In that case, it would be positive semi-definite. Otherwise, it's positive definite. Okay, and this is the covariance matrix, which is equal to, what you do is take the sample average, x hat transpose, and do 1 over n minus 1, actually. But we have large enough of samples, so don't worry about why is it n minus 1? Unbiased is n minus 1 sort of n. 1 over n, x transpose x minus x hat transpose. And this is SPD for obvious reasons. Yeah, when n is large, it doesn't matter. Okay, so the first principal component is the direction along which the variance is maximized. Okay. The second principal component is an orthogonal direction. It's orthogonal to the first principal component, but it maximizes the variance in the orthogonal direction. Okay, that's the second principal component. By default, in two-dimensional data, it's the orthogonal direction anyway. So 2 dimensions, it doesn't matter what the variance along the second direction is. Anyway, so this is the second principal component. Now, these two can act as basis vectors since they're unit vectors. So if you treat these as the axes, as basis vectors, then this is what the data looks like. Now, since the axes of this ellipsoid are aligned with the coordinates, the covariance matrix is a diagonal matrix. So dimensions become uncorrelated. Okay. So this is when you use the PCs as basis vectors. Now, if you have, of course, it's a good thing that now the data points, sample points are uncorrelated. It was 2-dimensional, it's still 2-dimensional, but at least it's uncorrelated now. You have decorrelated all the sample points. But dimension reduction would happen if you have more number of dimensions. In that case, the second PC is meaningful. So you have let's say we have 3 dimensions. We want to choose a direction that maximizes the variance in a way that the direction is orthogonal to V1. And that would be the second principal component. And the remaining orthogonal direction would be the third principal component. Okay, so these are the sample points. And so now once we got the 3-dimensional data, this is what it would look like in 3 dimensions. But you can choose not to use the 3rd dimension. It'll be an ellipse, 2-dimensional ellipse, 2-dimensional data, but it would have a large variance along V2 as well. At least larger variance than along V3. Okay, so you can just choose V1 and V2, project the points along V1 and V2. Okay, how do we do dimension reduction? So the data matrix is X, whose rows are the transposed samples. And we find the covariance matrix. You can use my expression, or you can use MATLAB scope. And likewise, sample mean, you can choose, I think the command is mean. Mean will give you the mean of the samples. Covariance, and then what we do is we obtain the eigenvalues of V. Since the covariance matrix, eigenvalues of lambda. Covariance matrix is lambda. Okay, but it's not a diagonal matrix, by the way. It has they're correlated. The sigma 1, 2, sigma 2, 3, and so on, and they could be positive or negative numbers. Non-diagonal elements exist for this. Anyway, so we do find the eigenpairs of eigenvalues are not necessarily here, eigenvectors. And since this is symmetric, it's also SPD actually. It's symmetric positive definite. The eigenvectors would be mutually orthogonal to one another, right? So what we do is, this V1 is the first principal component. So take the covariance matrix, it's SPD, symmetric positive definite, and obtain its spectral decomposition. And the eigenvectors take the largest M eigenvector. Suppose we want to reduce the dimensions from D to M. Then simply take the first M eigenvectors. Okay, and this matrix W, whose columns are the first M eigenvectors. Okay, so V, I'm knocking off the right D minus M eigenvectors, columns, and then I get this matrix W. It's a D by M matrix. And X would be X transpose. Yeah, this would be n by, no, yeah. Y equals xw. This would be the n by m matrix instead of n by d matrix. D is the dimension and n is the number of samples. Now you get a n by m matrix. So these y's are sample points, n sample points in only m dimensions. Okay, so we accomplished a reduction of the total number of dimensions. Now let's look at how to deal with the homework. Please interrupt me whenever you have questions. Do you have any questions from the PCA?
So the PCA we are considering the first decomposition along maximum variance. So is that to retain the information? Like my intuition was depending on the variation of
the variations. So let's take the variation along V1. The variance would be sigma lambda 1. Okay. And the variance along V2 would be lambda 2. These are the eigenvalues of the covariance matrix.
Yeah, what we are choosing is along the maximum variance. So
Yeah, yeah.
First preference would be along the maximum direction which shows the maximum variance.
Yeah.
So the reason is we need to retain the input. Why are we choosing it along the maximum?
It's well, information is, there is a mathematical term, it's a mathematical concept, but informally, yeah, something like that. Informally speaking, yes. And you will see that in the homework. It's much better to how it will perform classification. In fact, I'll show you. Okay, so this is how we do let's get to the homework. So what I have is, these are my samples. Each sample is actually a face. So there are 10 people and 64, each person under high light, then gradually we reduce the light, and this is under very dark conditions. So under 64 different lighting conditions. So what's the total number of sample points do we have? 640 sample points. And each sample point is actually a matrix. Okay, so anyway, these are the sample points. Total number of sample points is 640. And we divide them into testing and training samples. So all the greens are the testing samples. Okay, but PCA will first find this W using only the training samples. Okay, so these brown ones are the training samples. And what I do is, I pick the first 3 lighting conditions, then ignore the fourth one. Fourth one is for, this is training and this is testing. Sorry, this is training and this is testing. I reversed it. Okay, so these are all the lighting conditions for all the persons. These lighting conditions are my training samples, and for testing, I'll use the rest, the green ones. Okay, so these two have been reversed. Okay, and there are 10 people, and we will call each person a label. So 10 labels, 1, 2, 3, 4 until 10. And so our purpose would be to, using PCA, to find a face recognition algorithm that would be able to identify for the test samples These test samples are oh, actually, I'm so sorry. This is correct. 4, 8. Oh, these are wrong. Sorry. So these greens are the testing samples. Browns are the training samples. So I'm training using less number of data points. Okay. So training sample indexes would be 4, 8, 12, 16. So this vector and this vector I've swapped. Sorry about that. Okay. So once again, the training samples are only 160. The testing samples are 480. The green ones are the testing samples. The brown ones are the training samples. What I've done is these should be, this vector should be 1, 2, 3, 5, this vector. I've swapped this and this. Okay.
Testing we are using, we are doing training with less or?
Yes, less. Let me correct it for you. So this is yeah, this fixes it. Okay, so this is correct now. So yeah, it's counterintuitive, but we don't need so much training samples. If we use more training samples, we'll be using most of the lighting conditions, right? We want to use less number of lighting conditions to do the training. And then for any lighting condition, we will be able to do the face recognition, identify what person it is. So we have labels are 10. So this is a 50 by 50 matrix, each sample. We have to convert it into a vector. 50 times 50, so it's this many dimensional vector. So this is the X1 is they are the training samples. And the testing samples are N2, 480 testing samples, 160 training samples. These are the training samples. And also, remember, there are class label attached to each of these training samples. Okay, person 1, then person 2, then person 3, until person 10. Testing samples, it's unknown what the class labels are. It's like we see a fresh face. Okay, which of these 10 people is it? And it'll do the recognition. Let's say we are doing some security detection algorithm, and there are 10 employees. We have several pictures of each of those employees. But when he's coming or she's coming, then we want to do whether it's one of those employees or it's an outsider, right? So, and that would be under any arbitrary lighting condition. So these are the testing samples. So this is what we do first, convert the matrices into rows. We don't have to do the centering in this case. For the simple reason, like it's between 1 and 0 and 255 or 0 and to 1, I forgot. Yeah, but negative, you don't have negative values for pixels, so just keep it like that. Or do? I don't remember because it's a vector anyway. We'll look at the MATLAB code. Then our purpose is to reduce it to 30 dimensions using principal component analysis. So in the code, it's called DPC. That's same as M previously. M number of dimensions was the number of reduced dimensions. I call it DPC in the MATLAB code, 30 dimensions, okay, from 2,500 dimensions, 30 dimensions. So then, after we've done the dimension reduction, in 30 dimensions, let's say we have 3 people. Okay, so these are the class labels. Okay, now we get a sample point. So these are the, along the reduced 30 dimensions, these are the sample points. And let's say we just have blue, green, and red. Unknown samples, we need to classify them. Okay, so using the same eigenvectors, the same W as we have to store the W that we got from the training samples, the W matrix. Okay, using that same W matrix. You don't recompute, let's say we have only 5 samples. We don't compute W over 5 samples, correct? Although I have this many training samples, 480 training samples, no, what if I had just 1 training sample at a time? I have to find the face. Okay, so coming back here, now I have, let's say we have this many samples, 5 samples, and now we have to determine if they are, which is the class label, red, green, or blue, or which of the 10 people it is. So these are the testing samples. And again, reduced dimension. In the original 2500 dimensions, this won't work. So the approach is k nearest neighbors is the general approach. I'm letting k be equal 3. So I'm picking k nearest neighbors of each of these. And you can kind of see intuitively why we want to preserve the variances. We want to maximize the variances. Otherwise, if one dimension, along one direction, the variance would be totally 0, then it's worthless for our classification problem. Here, we look at the Euclidean distances and then say, okay, these are the 3 nearest neighbors of this point. These are the 3 nearest neighbors of this new test sample. And these are the 3 nearest neighbors of this, 3 nearest neighbors of this. Then we do the classification. So we ignore the rest and then look at only the k nearest neighbors, where k equals 3 in this case. And then we can, the majority is whichever class label it has, that will be the class label of this one. Okay. And now for tiebreaker, this is the k nearest neighbor classification. Now suppose here, let's see, there are 2 blues and 1 red. But since there are 2 blues, the majority is blue. So this is classified as a blue. Likewise, this is classified as a green, although it has a blue neighboring k nearest neighbor. Okay, so this is quite far away, but it's classified from many stored sample points, training samples, but it's classified as green, and this is classified as blue. If we had, suppose there was one sample point which had red, green, and blue. Okay, then we would pick the nearest one, the single nearest one as the label. So k nearest neighbor is pretty simple. There are other ways to do tiebreakers for when we have more number of class labels and k is higher, but don't worry about that. Okay, so this is what I do. So D is the number of dimensions, which is 2500. NP equals 10. Number of people, number of class labels. And L is the number of lighting conditions. And the total number of sample points is 640, which is NP times NL. K equals 3, K nearest neighbor. And DPC is the number of dimensions we must reduce the sample points to from 2,500 dimensions to only 30 dimensions. And so L1 and L2, these vectors, these are the 4, see I've written it here, L1 vector equals 4, 8, 12, 16, check it here. L1 where was it? L1 is, are they the same or different? Oh, these are the training samples. 4, 8, 12. Yeah, oh, so this should be L1 vec and this should be L2 vec. Yet another one type of change. So this is L2 vec and this is L1 vec. Okay, so this is what I get. Okay, these are the indexes of the lighting conditions. Okay, and then N1 equals NP, number of people, 10, which is number of class labels, times number of elements. So L1 vec is how many do we have here? $16, yeah. 16. So 10 times 16 is 160, right? So N1 is the number of training samples, and X1 that's the matrix of training samples. Okay, the X previously upon which we do the PCA, and P1 is the class labels, which person it is, and that this read faces subroutine will return to you everything. It also returns lighting conditions, but we don't need that. We only need faces and the IDs of the people, the class labels. Okay, and then, so this is what you have to do here. So find the covariance matrix and then obtain the eigenvectors, do the spectral decomposition and obtain, you'll get the W matrix. And then reduce it to 30 dimensions. This would be 30 times 1600. No, how much would be 30 times 2500, sorry, right? Oh, no, sorry, that would be W. So Y1 will be 30 times 2500. Yeah, 30 times 2500. No, 30 times, sorry. Sorry, it will be 160 times 30. 160 times 30. 30 vectors, yeah. Okay, so 160 times 30 would be Y1. And then what I do is, I then do the same thing with my testing samples. I get Y2 testing samples in reduced dimensions, and then this is my nearest neighbor classifier. I think I accidentally deleted one line where I actually use the class labels P1, okay, and X1 to obtain this classifier. See this model, okay, this is based on the nearest neighbor approach. So this was done using this P1 and X1. X1 were the training samples and P1 were the corresponding class labels. Now, we don't know the class labels of the test samples. We pretend we don't know. We actually have it. So this is what it would predict. But the actual values are P2. Just like here, we had P1 were the class labels of the X1, or after dimensional reduction of Y1. Okay. Likewise, Y2, the corresponding class labels will be P2. Okay, which we have read off here. Did I didn't write that part of the code either. I probably should have. But I again read faces using L2 vec, and then I'll get X2 and P2. And N2 would be NP times number of elements of L2 vec. Okay, and then what I do is I compare the predicted, what does this classifier do? These are the labels that it would assign based on the k-nearest neighbor algorithm to the test samples, and then I count the number of times they're equal. That's the number of times the classifier did it correctly, and wrong is the number of times the classifier did not predict correctly. Where P2 and Ppred predicted class label and the actual class label are different. And then this is classifier table. It's called a confusion matrix actually. Also, for each person, I find the number of people who are classified along each as each. So each row would have number of corresponds to one person, and then each column would be how many times the person was classified as each person. P1, person 1, person 2, person 3, person 4, until person 10. So person 3 would be classified as person 3 most of the times. So the diagonal elements of the confusion matrix would be very high. Any questions? Did you understand the problem now? Okay, so with this we will end today's review. A couple of points. The exam, I will separately tell you what the format of the exam will be. It's already there in my in the handout that I gave in the first lecture. It's online. Schedule, syllabus, and whatever. And it's already there in the schedule. It'll be right after the spring break. After you complete homework 2, A2. There will be a take home, and there will be a synchronous online quiz that everyone has to take at the same time. Okay, and for the take home, part of it would be to do Fisher's linear discriminant analysis. Actually, it would be, you will use this code that you develop for this one, and then do FLDA for that. It will be a combination of both. Okay. So you will have to reuse what you already did. And if you did the PCA correctly, you'd get more than 80% of the time it'll do the classification correctly, which is quite an accomplishment given the phases. If you look at the kind of data that we have, like even I wouldn't be able to say, okay, this guy is this guy or this guy is this guy. But the classifier does it accurately 80% of the time, only using PCA and nearest neighbor classifier. If you use PCA followed by LDA, I think it gets to 9 dimensions. Yeah, 9 dimensions for 10 faces. You have to reduce it to 9 dimensions, and then do nearest neighbor classifier. It will give you 90% accuracy.
Multi-dimensional scaling. I think you posted multi-dimensional scaling lectures after PCA.
Not LDA?
No.
Oh, I'll change that. Okay, well, sorry for that. I'll change that.
Just after the link for PCA,
Mhm.
it was this multi-dimensional scale.
Oh, okay. Did you look at that?
Yeah. I mean, I started looking at it, I thought it would come after.
Oops. Anyway, we will end this lecture.